Hello and welcome to this Sussex Universe lecture. Today we have Dr. Yuliya Kyrychko, who is going to walk us through the world of epidemic modelling.
Hi everyone, thanks for tuning in to this talk. I hope you're all safe, well, and are looking forward to knowing all about modeling. So what I want to do today is just sit, enjoy, take notes if you want to, don't take notes if you don't want to. If you have any questions, there will be live question and answer session after the talk, so stay tuned until the end, where I'll be answering your questions, and I hope we'll have nice and lively discussion. Now I should mention that although I'm used to teaching large classes and giving presentations at conferences, etc., this is my actually first ever recorded presentation, so bear with me. Before we start, a little bit about me. So currently I'm a reader in mathematics at Sussex Uni. But before, some time ago, I was born in Ukraine, in Dnipro, where I also did my undergraduate degree in mathematics. After finishing my undergraduate degree, I moved on to do an MSc, and during this time, I went as an exchange student to Germany, to Brandenburg Technical University in Cottbus. So I was there for 1.5 years, and after finishing that one, I came to University of Surrey to do a PhD in mathematics. And it's actually during that time of my PhD that I became interested in applications of mathematics to real life, and in particular to modeling of epidemics. And my first ever research paper on epidemics actually came out during my PhD. And so, driven by this interest in applications, I was fortunate enough to secure a postdoctoral research position at the University of Bristol, where I was involved in modeling of engineering applications. So I was in Bristol for 6 years, and then after spending a very enjoyable and interesting time in Bristol and learning a lot of modeling things and techniques, I came to Sussex in 2010, where I was hired as a lecturer, and then I was promoted to senior lecturer, and then a couple of years ago to a reader in mathematics. And this is where I currently am. So what I do, I teach undergraduate and postgraduate students, I supervise PhD students, and I also do my research in this lovely place with an amazing campus. And in particular, I'm teaching a module which is called Introduction to Mathematical Biology, and part of that module involves modeling of epidemics. So if you want to know more details, etc., sign up to Sussex, come to my module, and you'll know everything. So before we start, I want you to get ready. So either get your comfy chair or get your steps. If you haven't done enough steps today, you can start walking, you can start doing exercises, or you can just take your kids, sit down on a comfy sofa, and enjoy the talk. If you want to make notes, take out your notepads. This talk will be obviously available online, so you can watch it as many times as you want and make notes either now or later, or don't make any notes. And then I think it's always very important to have your favorite drink with you. So whether it's tea and coffee, or gin and tonic, or a little bit of milk. This talk is suitable for all ages and all levels of mathematical knowledge. You don't have to know anything in advance. I'll explain everything as we go along. So sit back, enjoy, and prepare to ask me a lot of questions afterwards. Let's have a brief overview before we start on modeling. So it was early December of 2019 when the first case of COVID-19 was reported in Wuhan, China. And although it was just an isolated case, it very quickly became apparent that in order to contain this pandemic, we need to do something. And in particular, since this is such a contagious disease, on 23rd of January 2020, Wuhan was placed on full lockdown, so people were not allowed to go outside or do normal day-to-day things. And we were all hopeful that it will stay this way for a little bit, and then China will relax lockdown and everyone will be safe and fine. Now what happened next, we all know. So on 9th of March, Italy went into lockdown, and then it was followed by Spain on 14th of March, and then it cascaded to across the board. So a lot of countries went into lockdown, so UK, US, etc. And just look at number of people placed in lockdown. It's mind-boggling. We have millions and millions of people just staying at home and protecting ourselves, but also protecting other people by not socializing or going out too much. And while this is a very concerning and sad situation, actually it allows to spend a little bit of time on writing public talks or interacting with public about modeling or actually doing research on COVID-19. So what do we want to do? What we want to do is we want to look at this problem of COVID-19 epidemic. We want to somehow think about it and then reformulate it in such a way that we can write it in terms of mathematics. Now, how we do that, I'll show you in a second. So first, the concept is take a problem, think about it, and then try to formulate it in terms of maths. Now, when we are thinking about modeling, we need to distinguish between different concepts, and in particular, for example, between what it means to have a linear function or non-linear function, linear equation or non-linear equation. So what you see on the screen is a very simple equation. It's a linear equation. Now you probably remember from school, or you've just learned in school, or you haven't learned at all. But just to remind you, linear means, so for example, if you look at this x next to 5, so we have 5x plus 4 equals 12. So this x has actually power of 1. Now this power of 1 means that this equation is linear. And since this equation is linear, we can quickly rearrange everything and we can find the solution to that equation. Easy, simple. So linear equations are usually pretty simple to solve. Now, when we have a non-linear equation, something else is happening. So if you look at the equation at the bottom of your screen, so we have x to the power 6 plus 75 x to the power 5, etc., etc., etc. And suppose we want to solve that equation. So if you want to solve that equation, we obviously want to find x. Can we find x? Well, the problem is, unlike in the previous example where x was to power 1, now we have a highest power which is 6, and then it goes on and on and on. And actually, it's not that easy to solve such an equation, and sometimes it's even impossible to do so. If you're lucky, we can use computers and try to find an approximate solution, so not exact, but an approximate solution in cases of nonlinear equations, if those solutions exist. So the first thing we have to remember, which we'll use later on, is linear versus nonlinear. Linear is where highest power is 1, nonlinear is everything else, basically. So if you want to plot linear or nonlinear or exponential, and this is where this exponential distribution or exponential growth comes from. So if you look at top left corner, what we have this wiggly line, and this wiggly line is a nonlinear behavior. Now everything at the bottom, so pink and dark blue, dark green squares are actually examples of linear behavior. And then the most striking one, and sort of most frequently used in headlines and newspaper coverages lately, is an exponential growth, where you can see this little arrow which is shooting up. So let's discuss what we mean by exponential growth. Now we've heard that number of cases is growing exponentially, and we need to do something. We need to stop this exponential growth, because This is very dangerous and healthcare systems will not be able to cope. So let's forget about healthcare systems and number of cases of COVID. Let's concentrate on exponential growth itself. So for example, we have function which is a y equals to 2 to the power of x. And suppose we go through x and calculate y. So when x is equal to 0, y is equal to 1. Easy. When x is equal to 1, y becomes 2. When x is equal to 2, y becomes 4. So we can see that very quickly we are going from 1 to 2 to 4 to 8. And if we continue this, then what we'll see that if you go up to 10, just up to 10, we get into thousands. And this is why exponential growth is kind of dangerous if you are talking about epidemics. It's actually not very nice if you have a mortgage or a loan and interest rate is calculated using exponential growth. Very quickly, if you fall behind payments, you will end up in huge debt. So let's plot how the exponential function looks like. So what we see this red line which is starting fairly slowly and then very quickly it shoots up. So what it means is this is one of those unique functions where the bigger you are, the faster you grow. So as we increase horizontally, we can see that vertically we are increasing very, very fast. And this is why when we are talking about COVID and number of new cases, and we are talking about exponential growth, basically we are looking at this curve and seeing the number of infected people shooting up. So let's do modeling. Now we know, so we know about linear, we know about nonlinear, and we now understand exponential growth. Perfect. That's all we need in order to start our modeling. So for modeling purposes, what you need to make assumptions. Now bear in mind, when we are talking about modeling, we are actually talking about approximations of whatever processes we want to model. So for example, if you want to model epidemics, we need to make certain assumptions because we cannot take into account everything. It will become unmanageable and highly nonlinear. And we saw that when equations become nonlinear, we cannot solve those equations. So let's make assumptions. The assumption will be as follows. So we have person A, and person A is perfectly healthy individual running away from the virus. And we have person B, and person B is not so well, and person B is coughing and sneezing. And person A comes into contact with the person B. Now they may or may not infect person A. So this may or may not infect person A means we have some probability of infection. And this probability of infection is described by rate beta on your screen. So what we'll say that probability of person A meeting person B and getting infected is rate beta. So now let's think about our population in total. So we are not talking about any specific country. It doesn't matter. We can model populations of cities or population of countries or population of small villages. So what we do is we assume we have this population of some territory, and we'll divide the population into two classes or two compartments. First compartment will be number of susceptible or healthy people, and that compartment will be denoted as capital S. And then we'll also assume that we have some number of infected individuals in the population. And this will be denoted by I. So again, let's summarize. We have transmission rate beta, and also number of susceptible people and number of infected people. And usually you assume that number of susceptible people is much higher than number of infected people, especially at the beginning of epidemic. And now we could say that this is it and write down a model describing interaction of those individuals, or we can go further and make model slightly more realistic So now what we'll say that we have person A, and then we have person A who is healthy or susceptible, as we've discovered now. We have person B who is infected, so class I, and then we'll say that actually after going through infection, person A becomes healthy again, so recovers. So now probability of recovery will be rate gamma. So we go from infected into recover at a rate gamma. So rate beta is becoming probability of becoming infected, and gamma is probability of recovering. So let's go back to our notation and let's have a look what's happening there. So S denotes number of susceptible or healthy people. I denotes number of infected people, and now we have those people who are actually recovering. So people were unfortunate enough to get infection, but now they are fine. And this class of people will be denoted by capital R. And so memorize SIR. SIR is actually the model which is used, or which is a basis for all mathematical modeling of epidemics. SIR model because it's called susceptible, infected, recovered model. So in susceptible, recovered, infected, recovered model, what we do is we look at time evolution of 3 different classes. So we have class of susceptibles, we have class of infected, and we have class of recovered. And as time goes on, the number of people in each of those classes will be changing. So depending on each particular moment of time, there will be this or that number of susceptible or infected or recovered people. Now, when we are talking about rate of change, we are actually talking about a derivative. So derivative is rate of change or speed of change of population sizes. So in this case, population sizes of susceptibles, infected, and recovered. Now, derivative is denoted by this ds over dt, or di over dt, or dr over dt. And let's think what's happening to population of susceptibles. So remember, susceptibles are healthy people, and at rate beta, which is rate of infection or transmission rate, they can become infected, which means we have minus beta times s and times I. What it tells us that over time, number of susceptible people becomes less and less and less because we have fewer susceptible people left since infection is in the population. Now, in the second class, in class I, what we have people who are becoming infected, so the same beta Si, but now with the plus sign, because what we are saying over time we'll get more and more and more infected people. But also we are saying that actually some number of people will recover. And since you don't need to get into contact with anyone susceptible or infected or anything, in order to recover, we have minus gamma I in the second equation. And then the last equation is very easy. So last equation, dr over dt, actually describes time evolution or speed of change in population of recovered, and it's governed just by gamma times I, because basically recovered are all those infected people who are now not infected anymore. So they went through the infection, they got better, and they moved into class R. Now, remember we were talking about linear and non-linear. Now we were talking about linear and non-linear because if you look at, for example, beta times S times I, this quantity is actually non-linear because S times I makes that power, remember power of x was 1 or larger than 1. 1 is linear, larger than 1 is non-linear. And now S times I makes that power sort of 2, so it's non-linear. So that system of equations is non-linear. Now I'm saying system of equations because actually in order to find solution for S, I, and R, we need to solve all 3 equations at the same time. So once we solve all 3 equations at the same time, we can get the solution to the system. Before we do this, so just to remind, so what we are saying we have n, which is total population size, so everyone in the population, and obviously since we are dividing population into 3 classes, n is equal to s of t plus I of t plus r of t, and that's always the case. And now an interesting thing, so in order to solve differential equations, what we need something which is called initial conditions. So you have to start from where? From somewhere. Now let's think about initial conditions. So what are we actually saying? We are saying that we have class of susceptibles, and initially we'll say that there is a certain number of susceptibles in the region that we are looking at, and that number is S naught. So S of 0 means S at time 0 equals S naught. Now we also need some number of infected people in the population in order to start the infection. Obviously we don't want to, but if you want to model infections, we need even small number of infected people or individuals. So what we'll say that initial condition for I at time t equals 0 is equal I naught. Now when the epidemic starts, we don't have any recovered. So at time t equals 0, number of recovered people is 0. So what we have very large number of susceptible people, we have quite small number of infected people, and we have no recovered people yet because the epidemic is just starting. So hope this is clear. We go from class S into class I into class R, and in order to go from between those different classes and solve those equations, we need initial conditions, and initial conditions are on the screen. Now let's, as I said, when we have linear equations, we can solve those. When we have non-linear equations, and we know that these equations are non-linear, it's actually a little bit harder to solve, especially using pen and paper, but we can use computers and find solutions that way. So let's have a look what we have. We have dark blue line, and dark blue line or curve describes how the population of susceptibles evolves over time. So horizontally we have time, and vertically we are plotting solution S, solution I, and solution R. So what we can see that we are starting from very large number of susceptibles, and over time as epidemic starts or infection starts to spread in the population, number of susceptibles goes down. Now let's have a look at the black curve. Black curve is number of infected people. So obviously, as I said, when we start an epidemic, we have some small number of infected people, and this is where the black curve starts. And then as time goes on, so if you move along horizontally, what we can see that we have this bump up in number of infected people, and then eventually that number goes down. So this is quite an important curve. So when we are hearing about flattening the curve, this is exactly the one we are talking about. So black curve is the one we want to flatten. Now I'll talk more about this on the next slide, but before we go into next slide, let's have a look at the red curve. And red curve is basically number of recovered individuals. And as we've assumed in the beginning, we start from 0 number of recovered people, and then as time goes on, we get more and more and more recovered individuals. So this is the typical behavior of an SIR model subject to certain initial conditions. So the curve we want to flatten is exactly that black curve here, or a blue and red curve here. So if you look at this graph, we can see that horizontally we have time and vertically we have I of t. I of t means number of infected individuals over time. So when we are saying we want to flatten it, if you look at the, say, blue curve, we can see that we start from some number and then the curve shoots up pretty fast. Not only it shoots up pretty fast, but also it goes up quite high, which means that we are getting more and more sick individuals very, very quickly. Now, when we want to flatten it, what we are actually saying, we want to shift that growth in the beginning and make it slightly more flatter, but also we want to we want the peak of the curve to go down. Let's think what this graph also shows us. Basically, if you look at the area below the graph, this area shows number of infected people. Now, if you want to flatten it, we want to make this area to be smaller. So just flattening it and then having epidemic run for longer time will actually mean that we'll have the same number of infected individuals but over a longer period of time. So it's important to observe rules and stay safe and stay at home and not socialize even when it's sunny and nice, because we don't want this epidemic to go on forever. So let's, since we are all interested in when this lockdown will be over, when we won't have any infected people, let's go back to the equation for infected population. When we go back to equation for infected population, what we'll do, we'll say that let's start from time t equals 0. Now, why do we want to do that? Because we know the initial condition for I at time t equals 0, and that's I naught, and also initial condition for susceptible population, and that's S naught. Now, I naught is always positive, but if you look at the equation, at expression in brackets, beta S naught minus gamma, this can be negative or positive. And it's important whether it's negative or positive, because it will determine what happens in terms of number of infected individuals. Now, when is it positive or negative? Well, can be positive or negative depending on the relation between beta, S naught, and gamma. So what we can do, we can actually write those conditions on that expression in brackets being positive or negative slightly differently. So we can divide by gamma, and we'll get the condition which looks like beta S naught over gamma larger than 1, or beta S naught over gamma is less than 1. Remember, beta is our transmission or infection rate, S naught is our initial susceptible population size, and gamma is recovery rate. So if you look at this expression here and call it R naught, we have something which is called basic reproduction number. And this is a very important number, and I'm sure you've read a lot about it recently in the newspapers and heard a lot about it on the news. Because basic reproduction number, or sometimes it's called reproduction number, reproductive or reproduction number, is used to determine whether we have or do not have an epidemic. So what is it? Well, actually, basic reproduction number or reproductive number tells us about number of secondary infections coming from a primary source in a fully susceptible population. So we have fully susceptible population, we put one infected person in, and then we look at how many of the susceptible people that person infects. Obviously, this is different from infection rate. Why is it different from infection rate? Because infection rate tells us about probability of being infected. So even if we come into contact with a COVID infected person, not necessarily every one of us will get infected. Some will, some won't. And this is beta. R naught is actually how many people will become infected for sure. So, for example, there are different diseases and different R naughts. For example, for measles, R naught is 15, so it's a super highly contagious. But for such a disease as measles, we have vaccines, and by maintaining herd immunity, we are actually not facing huge outbreaks of measles epidemics. However, recently it becomes so it flares up from time to time. Now for COVID, R naught is between 2.5 and 2.6. Since we are talking about people, I've rounded it up to 3, which means each COVID infected person will infect 3 other individuals. And that's quite a lot, because when you think about it, so one person infects 3 people, and then each of those people infects 3 people, and it goes on and on and on, and then we very quickly have exponential growth we've looked at earlier. So as I said, basic reproduction number is a sort of golden number in terms of epidemic modeling, because it tells us, do we have an epidemic or do we not have an epidemic? Now, if R naught is less than 1, then we can say for sure that we don't have epidemic in the population. As soon as R naught becomes larger than 1, that becomes a problem, because then it means that we have an epidemic. And so having R naught between 2.5 and 2.6, as in COVID case, actually makes it pretty much in this state where we are facing an epidemic, and we all know that. So how can we reduce R naught? Because basically this is our way out of the epidemic situation. So let's go back at the definition of basic reproduction number. We have transmission rate, we have number of susceptibles, and we have recovery rate. So what we can do, we can reduce transmission rate. How can we do that? Well, we can basically introduce lockdowns, so we can stay at home, we can wash our hands, and infection rate will go down. We can also reduce number of initial susceptible people. Now, normally, if there is a disease for which there is a vaccine, that actually makes it much easier to reduce a number of susceptible people. Sometimes there are some diseases which occasionally provide cross immunity, or someone gets a disease in much milder form and then gets an immunity, so that reduces S naught as well. So those are ways of how we can reduce R naught so that it goes below 1 and epidemic stops. Now, we have this recovery rate, but there is not much we can do about changing that one. So you might think, okay, so why were we talking about exponential growth, and where does it come from? Well, suppose we are at the start of the epidemic, but not at time t equals 0. That means instead of looking at rate of change of I over time, at t equals 0, we'll look at time close to 0, not exactly 0, but close to 0, which means now that on the right hand side of this di over dt, we have I, which is function of time, times a constant. And we can see that it's exactly the same constant as before. Now, this equation is linear differential equation. Since it's a linear differential equation, the solution of that equation is either exponential growth or exponential decay. Now again, let's pause and think. Exponential growth in the number of infected individuals, not very nice. We can also have exponential decay in number of infected individuals, which is very nice. And that's all again governed by this beta S naught minus gamma relation. So if you look at growth of confirmed COVID-19 cases around the world, we can see that we go at a small number of cases for some time, and then the curve shoots up, and that shows exactly an exponential growth in daily confirmed cases, and that means in this equation here that expression in brackets is positive. Now, if you're talking about, so I showed you simple but very useful mathematical model for epidemics. Now, for COVID-19, there are some specifics which need to be included in order to make the model more realistic, although as a first approximation, SAR model works fairly well. So the main specifics of COVID-19 that we know of so far and are important to include into consideration are the fact that there is a period of time between someone becoming infected and someone showing symptoms of infection. So person A gets infected by person B, and then for some time that person can or cannot infect other people, but there will be no symptoms. Now the second is that we know there are some asymptomatic carriers of the disease, which means there are people who have the disease, they don't show any symptoms, but actually they can infect other people. That's also important to take into consideration because it will change infection rate. Now, what was also observed in many countries is that severity of the disease, so whether someone gets mild symptoms or more adverse symptoms, is dependent on the age, and the same is with mortality. So when modeling COVID, it's important to include age demographics into the model. And that means that actually using just 3 classes of an SAR model might not be enough to fully understand the dynamics of COVID. But we can expand the model slightly. So we can say that we can still have our susceptible class, infected, and recovered class. But now we have this additional E class, and E class corresponds to number of exposed individuals. So individuals who were in contact with an infected person, they got infected, but they don't show any symptoms yet. Also, what we can do, we can say, okay, we have number of susceptible people, and then that number of susceptible people will be divided into different subclasses. So say we'll separate everyone between 1 and 4 years old, 4 and 10 years old, etc., etc., etc. And for example, we want to introduce 18 different classes of susceptibles, just because they all will have different rates of infection, different mortality rates, etc., etc. And that's very nice because now the model becomes very well suitable for understanding COVID epidemic. But this is how the model actually starts to look like. So what we have not just 3 equations which we want to solve, but more than 700 equations which we want to solve. Now, 700 sounds like a huge number. It's possible to solve 700 equations and look at how number of infected individuals varies over time, how number of susceptible individuals varies over time, etc., etc. And obviously for that we need to use some numerical simulations, but it's possible to do. So I hope you enjoyed the talk. I tried to go through a simple but very powerful model, and also try to show you the flavor of what can be done in terms of COVID modeling. If you are interested in any modeling, do get in touch. I'll be happy to talk about this and help you if you are developing your own model, if I can, of course. And thanks for listening, and I hope you have questions, and stay tuned in.
Well, we hope you enjoyed this video. If you did, give the video a like, share it on social media, and subscribe to our channel to keep up to date with future uploads. And remember, if you're watching along with us live, the Q&A starts now at the Zoom link in the description down below.